The ideal gas equation, PV equals nRT, which is derived for an ideal gas, provides a really good approximation to a real gas at moderate temperatures and pressures that we are used to seeing in labs. But then if you take a real gas at situations that have something like high pressures or really low temperatures, in these cases, the deviations that the actual numbers from the real gas show from that of the ideal gas equation figures is really significant. It's really big compared to what you might expect. So let's try incorporating some additional variables, some additional physical quantities in the ideal gas equation to get a modified version of it that would apply to the real gas's case as well. So let's take an ideal gas first. That will be our comparison standard. So if you had an ideal gas I, then for that ideal gas I, you can write the ideal gas equation, and that will be P will just come out of here. Instead of V, let's write V sub I, the volume of the I gas. That is equal to N times RT. Now let's say you had the same number of moles of gas, the same temperature, the same pressure of a real gas, of a non-ideal gas. Then how will you incorporate the realness of this gas into the ideal gas equation? Well, for that, let's define the compressibility factor. And the compressibility factor, it's denoted by small z, since capital Z is reserved for atomic number. Small z, the compressibility factor, is equal to the actual volume of the gas that you have, the actual volume, divided by the ideal volume that should have been at those conditions. So V actual over V ideal. And let's try using this definition in this equation. So since this first equation is true, what we can do is, instead of having V ideal, instead of having V sub I, what we can do is we can write, if the volume of this real gas was capital VR, then we can write that Z in this case, small z, is equal to VR, that is the real gas's volume, divided by V sub I, so the ideal gas's volume. From this, do some rearrangement and you would arrive at V sub I, the volume of that ideal gas, is equal to the volume of the real gas divided by Z. Since this first equation was true, you can take this and you can plug it in. So instead of V sub I, you would write V sub R divided by Z. So when you do so, when you write that, so P times V sub R over Z is equal to nRT. Multiply by Z on both sides and you would arrive at P times VR, the ideal, not this time it's not the ideal gas volume, it's the real gas volume. This product is equal to Z, the compressibility factor, times nRT. And from here to here, the only change is in the addition of this compressibility factor. So let's explore what this compressibility factor means in a bit more detail. So as the name implies, the compressibility factor gives you an idea of how compressible, how much compressible the actual gas is compared to the ideal gas. So how much compressible the real gas is compared to an ideal gas at the same state, at the same conditions, compared to an ideal gas. And so if you went on and you made a graph of it, so what you would actually do is you would take, let's say, at a particular pressure and temperatures, the volume of an ideal gas, which you can figure out from here, you can find the ideal gas volume, this V ideal, and you would measure experimentally the V actual, and you would divide that and you would get the value of your compressibility factor. A quick note though, instead of having V actual and V ideal, we can also have the molar volumes. So by molar volumes, we mean we will just divide both the numerator and the denominator by the number of moles. And this gives you not the volume, but the molar volume. So compressibility factor, yes, it is equal to V real divided by V ideal, but it is also equal to the molar V real divided by the molar V ideal. These both are the same. The molar volume is just the volume of 1 mole of that gas. And since the molar volume for any ideal gas is fixed at a particular pressure and temperature at some P and T, the only thing that changes is this volume. Now, if you had 2 gas particles, so let's say this is the bunch of nuclei, the positive charge at the center, and then you have the electron cloud. So let me do electron cloud in blue. And then you have, let's say, another particle, another molecule slash atom, and again, a positive centered nucleus, nuclei, whatever it is, covered by an electron cloud. Now, this is a very general representation of what a gaseous molecule will look like. At really, really far distances, if this was really, really far, if this distance is r and r is large, then the only forces that attract between these come from the attraction between this positive nuclei in the first particle and the electron cloud in the second. And the other would be the attraction between the nuclei or nucleus of the second with the electron cloud of the first. So if r is large, attractions are dominant. Now, if you start bringing these closer, so if I erase some of this, and I start bringing these, let's say I brought 2 a bit closer, so 2 will come somewhere here. Now at this stage, there are 4 forces acting. What are those? So the electron clouds on both of these, the 1 and the 2 electron clouds, they both will repel each other, since negatives repel each other and positives also repel each other. So likes will repel and unlikes will attract. So negative repels negative and positive repels positive. And similarly, by the same logic, the nuclei of these atoms or these particles, they will also repel. At a certain distance, that repulsion will become significant. So there will be some other repulsion as well between these. And then there are the attractions that we looked at in the first case. So this nuclei or nucleus will attract the electron cloud of the first. This one will attract the electron cloud of the second. So there are 4 interactions playing. And let's say at this R naught, attractions and repulsions cancel each other. Attraction equals repulsion. Let's take that to be a hypothetical place. If you bring it even closer, then you can guess that attractions are now recessive. The repulsions are now dominant to the attractions. If you bring them really, really close together, you really stick them on each other, the attractions almost cease to exist. They do exist, but their magnitude is pretty insignificant compared to that of the repulsion that's taking place in this scenario. So if r is very small, repulsion is dominant. Now, why did I do this? The reason for that is if you increase the pressure, while it's not sort of a direct consequence, but you can think that if you increase the pressure on a gaseous system, the distance between two gaseous particles will decrease. So eventually, if you started out with zero pressure, and I have a graph right here for all or for some gases, so I have nitrogen for methane, for hydrogen, for oxygen, for carbon dioxide. So for these gases, if you started out with zero pressure, so in other words, you had an infinitely long piston and you had really, really low pressure being applied somewhere, and these gaseous particles, they are not under influence of any pressure, and they almost behave like an ideal gas. So at this point of time, when you have really, really low pressures, at that time, VR over VI, the compressibility factor in that case, is very, very close to 1. And that's what we see here. This is the compressibility factor. And for really, really low values of the pressure, so let's say up to this bound, the compressibility factor lies in a pretty good range, pretty close range to 1. But as you increase the pressure, what eventually happens is you start to get some attractions, since now there is some upwards force. So let's say that the piston pushes from up, and attractions come into play. Now, it's not true that attractions will come into play for every molecule, for every entity that you have, but let's say if attractions come into play, let's say for carbon dioxide, two molecules of carbon dioxide start attracting each other in some ranges of temperature, and you can see in what ranges of in some ranges of pressure, and you can see in what ranges of pressure that happens. So since attractions are there in the case of some values of the pressure, the V real in that case is going to be lower than the V ideal. That's the whole point of having an attractive force acting. And so then VR over VI, the compressibility factor, that's going to be lower than 1. And so that's what you see for carbon dioxide. But after a certain limit, let's say for carbon dioxide, that limit occurs at 570 ATMs, just cooking up the numbers. If after 570 ATMs, the molecules come in sufficiently close contact that they now start repelling each other, then the volume of the real gas will become larger than that of the ideal gas, since repulsions are taking place if you increase the pressure even more at higher pressures, there will be lower distances between two gaseous particles, and that will mean there will be more repulsion, and that will mean that the volume of the real gas is greater than that of the ideal gas. And so what that means is that eventually, after a certain threshold, VR over VI will be greater than 1, and that's what you see for these gases. After reaching certain threshold, they all have a value of Z to be greater than 1. For a gas like hydrogen, repulsive forces are the only forces that are dominant. So from the very, very starting, from the very, very initial pressure changes, you see that the hydrogen's graph for Z against the pressure, that's always staying above 1. So that means for hydrogen, repulsive forces are dominant throughout increasing the pressure. Repulsive forces are dominant. For these gases, for certain range of pressures, like if you consider this blue line, so that's for nitrogen. So let's say for nitrogen, in the pressure range of 0 to let's take it to be 220 ATMs. In this range, the value of the compressibility factor is less than 1. So that means that attractive forces are more dominant.